Now we'll focus on the concepts of work and power. Work is the process by which energy is transferred from one system to another. And work is done when a force is applied over a distance. This is one of the most common definitions for work. So our first equation is going to be work is equal to force times distance. For example, if you were to push a block with a force of 2 newtons for 1 meter, you would have done 2 joules of work on this block. Remember, a joule is equal to a newton times a meter, or a newton meter. If this force were to be applied to the block at an angle, then the work done would be equal to the force times the distance times the cosine of that angle, theta. To explain this, I'm going to draw it out. So if we have a block and it moves a distance d, but the force is being applied at an angle theta, then we just need to take the horizontal component of that force F. So using trigonometry, we know that the horizontal component of that force is equal to force times cosine of the theta. So our work is equal to force times cosine of the theta times the distance, d. Now we're going to talk about the work energy principle. The work energy principle states that net work done is equal to the total change in kinetic energy. So we know that net work is equal to delta KE, or kinetic energy. Delta just stands for change in. So the change in kinetic energy is just equal to the kinetic energy finally minus the kinetic energy initially. Another useful way to think about this principle is its relationship to potential energy. When you're doing work against a continuous force, take for example gravity, work done is equal to the change in potential energy. So we know that net work is equal to negative delta potential energy. This can come in handy when thinking about lifting something. When you're lifting something, gravity is a force resisting you, and you do work to lift that object to bring it to a higher potential energy. The next thing to consider is power. Power is simply work over time. So our equation for power is equal to work divided by time. The more work you do on an object in a certain amount of time, the more power you output. And the faster you do that work, the more power you output. The units for power are watts, which are just equal to a joule per second. So let's do an example problem involving all of these concepts. Let's say we have a train of mass 3,000 kilograms moving across the track at 30 meters a second. A gust of wind comes and blows the train, speeding it up to 40 meters a second, and then it stops blowing. How much work did the wind do on the train? And for part B, if it takes the wind 15 seconds to speed the train up, how much power did the wind output? For this problem, we're going to ignore friction and wind resistance. So we're going to use the work energy principle to find out how much work is being done. Let's start by calculating the initial and final kinetic energies of the train. So we know that kinetic energy is equal to 1/2 mv squared. So now we're just going to plug in our values. So kinetic energy initially is equal to 1/2 3,000 kilograms times 30 meters per second squared. This is equal to 1,350,000 joules. Now that's kind of a big number, so to simplify it, I'm going to change it to megajoules, where a megajoule is just 10 to the 6 joules. So we get 1.35 megajoules. Kinetic energy finally is equal to 1/2 3,000 kilograms times 40 meters a second squared, which is just equal to 2,400,000 joules. Again, to make the number a little bit more manageable, I'm just going to change that to 2.4 megajoules. So we know that net work done is equal to delta kinetic energy, which is just equal to 2.4 megajoules minus 1.35 megajoules, and we get 1.05 megajoules. And that's our answer for part A. For part B, we're looking at power. Power is equal to 1.05 megajoules over 15 seconds, according to the equation. And if we do that, we just get 0.07 megawatts. And to make that number a little bit more manageable, I guess you can change it to kilowatts, which are just 10 to the third watts. So I just move the decimal place 3 spots to the right, and I get 70 kilowatts.